Control chart limits have to be appropriate with respect to the natural variation in the process. When we don't happen to know what that natural variation is, we have to estimate it before we can design the control chart. If we have to estimate it, that means we're going to need a considerable amount of data on which to base that estimation, and you can see that shaping up in this scenario. Let's look. The production manager feels that main house gaming should treat natural process variation as unknown. We'd been looking at this previously, treating it as it was known, but nonetheless, that's what's different now. Samples consisting of 4 round tiles. Now, it's always good to note this. Samples consisting of 4 round tiles means, don't forget, lowercase n is always the sample size, n equals 4. All right, were gathered when the machine was known to be operating correctly, cutting 20 millimeter round tiles. So this big block of numbers in here, these are observations. You can see that what we have done, just scanning that block of data here, is that we've gathered 10 samples. We've gathered 10 samples and we have calculated, because look at the outside column, we've actually calculated what the mean diameter was in each sample, and this is good. This is good. This is going to be very, very helpful. This right here is what we would call X bar. These are the X's, X bar. These are the sample means. Now, notice that it says what would be the appropriate mean and range chart. All of a sudden, we're talking about 2 different charts. What would they look like to monitor this production in the future? We have formulas for upper and lower control limits, except we have 2 sets of formulas because we're actually being commissioned to create 2 charts. Now, wait a minute, why 2 charts? Hang on to that thought. First off, the mean chart is familiar to us. Oh, okay, now wait a minute, I think we can start filling in this formula, except see that the first thing that this formula asks for is not X bar, but X double bar. Oh, that is really easy to find from these observations. X double bar is just average of the averages. So right away, first off, in order to complete this work, why don't we first find X double bar, the average of the averages? Just take this column right here and average these numbers. Average these numbers, I did that, I got 19.92 millimeters. Okay, now save that thought because that goes here and that goes here. But well, what is the rest of this stuff? Oh, all right, actually what we just found is we found the center of the mean chart, if you will, kind of the dotted line, the center of the road. We could even lock that in. If you have the note frame on the next page, there is a blank chart to start developing. Might as well start labeling it. The center would be 19.92, but what would the upper control limit, what would the lower control limit be? What is this other stuff? Oh, all right, we found the center, but we started out this scenario by saying that we're not confident that we know exactly what the natural variation is. We're going to have to estimate it. Now, what is going to stand in, so to speak, or substitute for specific knowledge of the standard deviation and the natural processing distribution? Okay, range. The first thing we want to know is what is the range in each one of these samples. Now wait, say what? Range? Yes. So we're layering in a new concept. Sample range, or capital R. And it's very easy to calculate. The range in any sample is nothing more than the largest observation minus the smallest observation. Oh, okay. So, like for instance, for sample 1, I'm looking up here across the top. If I wanted to calculate the range, I would just scan. These are the individual observations, or the X's, so to speak. I'd say, which one's the largest? Oh, it's 20.01. Okay, 20.01. Which one of these is the smallest? It's 19.95 minus 19.95. Okay, I get 0.06. Yes, that is range in sample 1. Okay, but you know what? I don't just need the range in sample 1. Okay, here's the work. I need the range in each one of these samples. The easiest thing to do would be to make a whole nother column. So that's what I'm going to get set up to do here. I'm going to draw some lines first, just so my work stays neat, because there's 10 samples. And I basically got to process this data that's been gathered in order to estimate the natural variation in the process itself. So I create one line for each sample. Might as well extend that one here at the top. Right there, because it's time to calculate range. It's time to calculate range. We have the range for the first sample. We did that for demonstration. That is 0.06, and then we just keep going for each one of these. For instance, for the second sample, who's the largest? So it's a 20.5. Who's the smallest? It's a 19.97. Yes, that's a range of 0.08. Same process here for the third one. Who's the largest minus who's the smallest? I get 0.07. Then for the fourth sample, I get 0.12 millimeters. And then the next one, 0.08 millimeters. And then the next one, 0.09 millimeters. And then the next one, 0.13 millimeters. And then the eighth one, I get 0.08 millimeters again. And then the ninth one, 0.10 is the difference between the largest and the smallest. And then on the bottom line here, who's the largest? Again, 20.01. Who's the smallest? That 19.94 is a range of 0.07. Oh, all right. Now, say, fine. What am I supposed to do with this? Average it. See this parameter here that we need? R bar is just average range. So in our case, those numbers, now that they're found, just average them. R bar, I got R bar 0.088. 0.088. Great! I have found this parameter. We have almost everything that we need to start drawing control charts. For instance, in the case of, this is the formula for the mean chart, and this is the formula for the range chart. In the case of the mean chart, which we actually started drawing on the next page, the only thing that we're missing is one other parameter. It just says A2. Okay, A2. Where do I get that? Oh, you look it up. If you are drawing up a chart for a process that you don't, in fact, know what the natural variation is, so that you're trying to gauge it, right, by looking at ranges in sample data, you do need a special chart. It is meant to help you estimate. Good place to put the limits. That's the chart we just flashed past it last time that is printed on the next page. You see mean chart right there, and a whole list of different values you can use. Which one are you supposed to use? Look up the size of the sample. Look up the sample size. Never look up the number of samples. So the number that we're after for this particular problem is going to be on this row, because we were remarking earlier that n equals 4, that they're going to pull 4 tiles at a time. Okay, that the rest of the numbers that we need to just finish this out and be done with it are going to be on that row, the row for 4. Before now all we have to do is fill out the formulas, actually draw the charts. Very common mistake, Some people would accidentally look up numbers here. Why the 10? Because, just don't be distracted, because there were 10 samples in the table. You don't actually do anything with that information, like the number of samples. Did you have 10 or did you have 30? It's the sample size. The size is 4. Oh, all right. Now we finally have everything that we need, because let's finish this mean chart right here. The upper control limit is x double bar plus A2 times R bar. Just fill it in now. X double bar, 19.92 plus A2. We said that it would be on that row. It says 0.73. That's the number you use. 0.73 times 0.088, because that's R bar. So I get 20.056 millimeters. That's the upper control limit. Found it. And then where is the lower control limit? Very similar scratch work, except subtract. So 19.92 minus our A2 factor times 0.088 equals 19.928 millimeters. That's where you should set the lower control limit. The average of the diameters of 4 tiles picked at random should not be any skinnier than that. There. Now we have the mean chart. So in the future, someone would use this, right? If they had, for instance, pulled sample 1. I mean, sample 1's actually history, but if they had pulled sample 1 in the future, it says sample mean 19.98. Oh, 19.98, that means that when they plotted, it would just be slightly above that. Right, and then if they happen to have pulled sample 2 in the future, oh, sample mean 20, okay, then it would also be, and they would go on plotting the average diameters of randomly picked groups of 4 tiles. Oh, no, wait, that's the mean chart. This problem commissioned us to draw 2 charts? Yes. When you don't know the natural variation for a fact, it is a good idea to maintain 2 charts, so in the future you can watch that issue of averages, but you can also watch the issue of ranges. We should draw the range chart as well. Now, range charts can be a little odd, because normally in a control chart we expect the center of the road to be in the center. On a range chart, not necessarily so. We had worked hard, we did all the scratch work to find out that the average range in the samples that we're working with was 0.088 millimeters. I am putting that on the chart, but I happen to know, and this is not uncommon with range charts, that by the time we're finished finding the upper control limit and the lower control limit, notice that that's not going to be exactly in the center. Oh, right, because we're now going to create a chart that they can also plot the ranges on in the future. Oh, all right. Oh, how do we do that? Wait a minute, we had the formulas for that. Upper control limit, and they're actually simpler formulas than any of the other control limit formulas. You just take the average range that you found here, right, and to find the upper control limit, you multiply it by something called D5 and the lower control limit by something called D4. Where am I supposed to find those? Oh, they're on that same row. Don't deviate from that row. Sample size of 4. There we go. Oh, so for instance, to find the lower control limit, take the range, lower control limit, take the range 0.088, multiply times 0. I mean, did I really need to write that? The lower control limit here is 0. Meaning that in the future when we plot the range in a sample, right, the range could go all the way down to as little as 0. And this makes sense. It's not going to bother us. It's not going to fall outside of the limits. The upper control limit, though, I do have to do a little bit of multiplication here. I can't do in my head 2.28. times 0.088, I get 0.201 millimeters. Yes. So now I have a chart that in the future, when they plot the ranges, right, they will tolerate everything from there being no range in a sample, which, yeah, they'd be they were absolutely identical, great, all the way up to a range of 0.201 millimeters. And notice we never did have any one of these samples that was ever had that larger range, and that would make sense because these samples were taken when this was in control. In the future, they would just continue to plot those ranges to continue to monitor the idea of both the average diameter, that's the mean chart, and the degree of variation around that diameter, that's the range chart.